Okay, let's get started. I don't know if 13 people have dropped the class, but we have 21 enrolled and currently 8 in the room. And some more are coming.
It's a Monday.
It's a Monday, fair enough. It's unfortunate that we have Monday and Friday, Monday and Friday right next to the weekend, but hopefully you had a good Valentine's Day break. So homework, what is it, 3? Homework 3s are up here. So we have 2 homeworks to go, and one's obviously this Friday, and then the next one's the next Friday, and then no more homeworks after that. So then what you should be thinking of at this point is a project idea. So only 2 people have sent me, I want to work on this project with this person, and I want to present on this day. Only 2 people have ever sent me anything. So remember that you have until, I think, March 2nd, somewhere around there, to submit a project proposal idea. And you have to actually do a write-up. So you have to write up what you want to actually do and submit it to me. Yeah?
Are the write-ups, should they be done like for everyone or just per group?
It's per group. Yeah, that's fine. It'd be easier to manage that way. Yeah. So each group, 2 or 3 if it would make sense for the project, or 1 if it makes sense for the project. Every group will send me a proposal by March 2nd, and then we can talk whether or not that is a reasonable project to do in a few months' time, or if it's not enough, if it's too much. If you need some kind of resource that would help you get started, we can talk about that. So all those sorts of things we can talk about. Okay, just as a reminder, it's on March 2nd, it's coming up, so start thinking about who you want to work with and what project you want to do. Okay, any questions about the project itself? Another reminder, we have 2 papers to read for this week. 1 normal length paper and 1 shorter paper. So make sure to read those for Friday. I expect more participation instead of just from like 2 or 3 people like last week. I expect more participation. Yeah, and one more thing about the homework. So a lot of you did really well on the homework, but quite a few of you, like I would say 30–40% of the class, got low scores on the homework because they didn't do what the question says to do. So if the question says like solve for n, it needs to be solved for n. If the question says produce a plot, you need to produce a plot, okay? So if you don't do what the question says, I can't help you, okay? Just on future homeworks, do what the question says. Okay, any questions otherwise? Okay, so we finished talking about greedy methods. So what are the things that we talked about so far? So we talked about exhaustive methods first, and then we started talking about exact methods, and then we just finished talking about greedy methods. In the sense of 1 row at a time methods. So these methods that we're going to talk about here, anti-random and IPO, so it's not initial public offer, it's a different IPO. So so here they are in a sense 1 row at a time methods, but not quite the same. So whereas before, for greedy methods, when we had the 1 row at a time method, we tried to do some local computation on the row that we're adding, and that's it. Here we're trying to do some 1 row at a time calculations, but on everything that we've done so far. Whereas what we did before is only on the row that we're adding. Here, what we're going to do is focus on all the rows that we've ever made and then try to make a greedy decision based off of that. So let's talk about the first one, which is anti-random. So if I were to make, say, these tests, so let's just say I have 5 zeros, and of course I'm not going to make a duplicate because that would not be useful to me. So let's just say I make a row of 4 zeros and a 1, and 4 zeros and a 2, 4 zeros and a 3, and I continue in a similar type way. So let's just say I make rows like that. So, and let's just say, for example, t is equal to 2. So fewer than the number of columns that I have. If it was 5, then there's nothing I can do better than that. But if t was 2, then what do you see is kind of annoying about these tests that I'm making if t is equal to 2? So if the strength is 2, what do you notice about these rows that we're making here? There's a lot of repetition. So if I pick, say, the first and the second column, then I'm going to see 0, 0 a bunch of times. If I pick the first and third, or the first and the fourth, second and third, or third and fourth, I'm going to see the same thing over and over and over. So what anti-random is all about is, it's not about being deterministic. It's about trying to avoid this type of thing. So it's not equivalent to saying that this is not random. That's not the way to think about this. So anti-random is basically a pseudonym for let's be strategic about this. So the way that we're trying to do this is let's try to make the tests as different as possible from everything that we've seen before. So to try to minimize the amount of repetition that we may see. So for example, so let's just say for the moment that we have strength 2 and 2 symbols, for example. Well, if I haven't made any tests yet, then it doesn't really matter what the first test is. So I might as well just pick all zeros for it. Well, if I want to minimize the amount of repetition in making the second row, what could I do? Well, there's a lot of things I could do. But one thing is to try to make the test, the row that we're going to add, as different as possible from the first one. So what is the row that is as different as possible from the first one in this case? Yeah. It's just all ones. So if I have a row of all ones, then any interaction in the first row doesn't appear in the second one. So the interactions covered by the first row and the ones covered by the second row, there's no repetition between them. So that means that in the first 2 rows, we're doing as good as we possibly can, which is pretty good. So then you may think, well, what we need to do is then we need to make the 3rd row, then the 4th row, etc. Well, if I only have 2 symbols here, there's no way that I can make the 3rd test right here completely non-overlapping with the previous 2 tests, because I only have 2 values that I can work with. So let's just say, for example, that I pick a 0, 1, 0, 1, 1 or something. So no matter what happens, I have to have some repetition now, because I'm involving values that have appeared previously. So what I would need to do here is I want to pick a test that is as different as possible from the previous ones. Okay? So that is what is called Hamming distance. So how many of you have ever heard of Hamming distance? Okay, so it's pretty simple. So the idea is the notion of a row being different is just the number of places in which it is different. So if we look at the first two rows, for example, then how many places are the first two rows different from each other? In how many positions are they different? 5, yeah, because the first column they're different, second column they're different, third are different, fourth are different, fifth are different. Okay, so because they have length 5, then that means that these two rows have maximum Hamming distance possible because they're completely different in every position. So let's look at the first and the third rows. So how many places are the first and the third rows different? In 3 places, namely in the second column right here, fourth column, fifth column. So that means with this pair of rows, they have Hamming distance 3, the number of places in which they're different. And likewise, if we look at the second and the third rows, we see that the Hamming distance is 2. So, namely in the first and the third position, because the second row is all 1s, the row we are attempting to add has a 0 in 2 positions, so they differ in 2 places. So what we want to do is to pick a row that is as different as possible from the other rows. So there are 2 ways you can actually go about doing this. So you could say, I want this to be as far as possible from everything else by just picking the row or a row that has the maximum minimum Hamming distance. You understand what that means? I can go over it. So look over every single, so let me just write it out. So this one says, so among all possible rows, determine the minimum Hamming distance, and then choose a row with the maximum, distance. So what we would do is, say for 0, 1, 0, 1, 1, the row that we're adding here, I look at the Hamming distance from the first row, then I look at the Hamming distance from the second one, so every row beforehand, I just record what's the minimum among all of them. And then, so 0, 1, 0, 1, 1 has minimum Hamming distance 2, because the first row has Hamming distance 3, the second row has Hamming distance 2. Okay, so then I would record Hamming distance 2 for this row. Then I would look at all the other possible rows that I could place here. I just record what is the minimum Hamming distance. So some are going to be 0, some are going to be 1, some are going to be 2, maybe some are 3. And then I just pick a row that has the maximum among those minimums. So I record all the minimums, pick the row with the maximum Hamming distance. So if there's some row that happens to have 3, I don't think there is one in this case, then I would pick that one. And you can actually show that for this third row, the best you can do is 2. But yeah, so that's the best you can possibly do. So then I just pick a row with maximum Hamming distance, place that row in, and then go on to the fourth row. Yeah.
I'm kind of confused because isn't the Hamming distance relative to, because like the Hamming distance is relative to for somewhere that you're looking at. That's relative to some other row that came previously.
Yeah. So In this row that we're adding right here, this third one, I just look at the previous rows, and I record the Hamming distance for each of the previous rows. And whatever the minimum is, I record that minimum number. So in this case, the minimum is 2 because the first row had a Hamming distance of 3 from this row we're adding, and then the second one has a Hamming distance of 2, so I record 2. So then I look at all possible rows I could place in that third row, and then I record the minimum Hamming distance among all of them. So if we do, let's just do another example. So if, for example, I instead do 0, 1, 0, 0, 0, then what is the minimum Hamming distance for this row that we're adding, this third row? Well, with the first row, what is the Hamming distance? 1. And the second row is 4. So what's the minimum? 1. So in this case, this gets a score of 1. And then the row that we had before has a score of 2, so it has it's more likely to be chosen. So then if I say I altered this to be 0, 1, 0, 1, 0, then this will have a Hamming distance of 2, a minimum Hamming distance of 2. So with the first row, it has a Hamming distance of 2. Second one has 3, but it doesn't matter, so 2 is the score that it gets. And then I just pick the one that has the minimum one. Any questions about that? Yeah.
So when we choose like the third row, like so, for instance, if we have like 0, 1, 1, 1, 1, 0, like the distance from the second one would be like 2, right?
So you mean this?
Yeah.
Yeah. So
is that also like
yeah, so it's just whatever the minimum is. Yeah. So with the first row is a Hamming distance of 3. The second row is a Hamming distance of 2. So the minimum is 2. So this row would get a score of 2. So let's actually do one more example. So if I fix this row into the array now by putting it in this color. So then now let's pick a row. So we have these first 3 fixed. Now I'm just going to pick a row. 1, 0, 0, 1, 1. I just picked that. I don't know if this is the max that you can get, but this is just what I picked. So with the first row, what is the Hamming distance? With the fourth row with the first row, what is the Hamming distance? It's 3 because the first row is all zeros and there are 3 ones in the bottom one. What about the second row? 2. And then the third row is 4. So the minimum for this row is 2. So this one would get a score of 2, and then I look at all possible rows and just choose the one that has the maximum. And then whatever's the maximum, I just pick that row, put it in, keep going until I get a covering array at the end. Another metric that you can go by is it could be that you have a row that we're adding that has really small Hamming distance with one row, but a gigantic Hamming distance with all of the other ones. So it could be conceivable that, like in this particular example, it has a Hamming distance of 3, 3, 3, 3, 3, 3, 3, and then one row has 1. And so the minimum is, in that case, is 1. So basically the minimum Hamming distance is throwing away all that good information about the other rows that had a really high Hamming distance. So another metric that you can go by is the total Hamming distance. So here you would determine the minimum Hamming distance. Oh yeah, no, sorry. So determine the sum of Hamming distances, and then choose a row with maximum sum of distances. Okay, so in a sense, the minimum was throwing away potential useful information. So like in this example that we just did, the fourth row and the third row have really high Hamming distance of 4. But because we chose the minimum, that threw away a bunch of information. So the sum here is basically retaining all of that information and carrying it along with you. I don't know if there's been any work in this, definitely not recently, but it might be worth looking into, even in some like limited scope of like some small parameters. What is the better choice in general? Is it the minimum or the sum? By looking at it through an exhaustive lens. Just try every possible row and then just see what happens. But it may be the case that there are a lot of rows that have that have the same minimum or the same sum of Hamming distances. So you may want to do this like a depth first search idea, where you say, oh, let's just choose this row for now, and then just see what happens at the end. And then maybe if this row is not that good, maybe we try this other row that has the same minimum or the same sum, and then try it with that one, and just see what happens. That might actually be worth looking into. So that's a good project idea. Yeah, so it's called anti-random because you want to be as far as possible from the other tests. Whereas with random, in expectation, the number of places that are different is fixed, because if you just choose 2 rows at random, you can calculate what the Hamming distance expected value is. Whereas with anti-random, you want to get the maximum every single time. Any questions on what anti-random is? Yeah, so the problem is, of course, how do you find the row, other than just searching every possible row? One heuristic is, let's just view this one row at a time. One value at a time. So let's just do the example that we had before. So these entries. Yeah, so what we can do is, let's just make a row right here, and I'm going to not fix the values to anything. So let's see. So I'm going to pick values one at a time for the new row. And the way that I'm going to do this is, I'm going to try to maximize the minimum Hamming distance, or maximize the sum if you wanted to, but I'm just going to look at the minimum for now. So let's see. So let's look at this first position right here. So it doesn't really matter what I choose in that position, because if I choose a 0, it's going to clash with the first row. If I choose a 1, it's going to clash with the second row. So let's just say arbitrarily I'm going to pick a 0 here. So it doesn't actually matter which one you pick, the first one. But now it actually will. So let's look at the second column. So here, I can choose a 0 or a 1. Well, let's see. Suppose I pick a 0 here in this position. So among these first 2 columns right here, what is my minimum Hamming distance? Just among those 2 columns. It's nothing, right? What if I instead chose a 1 in that position? What is my now minimum Hamming distance? It's 1. So which of the 2 is a better choice? The 1's a better choice. So I'm going to fix the 1 now in the row. Yeah, I know I deleted it. Okay, then let's look at the third entry. Well, I can either choose a 0 or a 1, so let's just pick a 0. Well, what is my minimum Hamming distance at this point? With the first among these three columns, I mean. So with the first row, it's 1. With the second row, it's what? 2. So the minimum is 1. So then if we instead pick a 1, then with the first row, we get 2. Second row, we get 1. So it doesn't matter which one we pick. Again, we can do this in an exhaustive way by just saying, oh, let's just try 0, just see what happens. And then we'll try 1 later and see what happens there and pick whichever one was eventually ended up being the better choice. So let's just say I pick a 1, just arbitrarily. Then for the fourth one, which of the two is a better choice, do you think? Well, if I pick 0, then the Hamming distance with the first row is 2. And with the second row, it's also 2. So again, it doesn't matter. Let's just say I pick a 1. And then now let's look at the final one.
Wait, let's choose one.
Should it be a 0?
It could be either. Because if I pick a 0...
Because you have a hand distance.
Yeah. I should have picked this. Yeah. They'll teach me to go quick. So let's just see. 0, it doesn't, I get a 2. I thought didn't matter mean didn't matter in the values. It meant didn't matter with respect to the Hamming values. So 0, you get a Hamming distance of 2. With a 1, what do you get? So the first row gets a 3, second row gets a 1. So 0 is the better choice. Thank you. Okay, then if we look at the fifth one, let's see if we put a 0 there. Then the first row gets a 2, second row gets a 3. If we put a 1, then the first row gets a 3, second row gets a 2. So now it doesn't matter which one we pick, I hope, unless I made a mistake. Okay, thank you. So let's just say I pick a 1. So then now that's a lot faster because I only have to examine 2 values for every single entry. Instead of just generating every possible row, I just have 2 values per each entry. So the runtime per row in this method is what? Well, if it's 2 things times the number of columns, well, that's big O of k, times the number of rows that we have seen so far. So it's k times number of rows so far, which is pretty good. Yeah, so that's the runtime per row, but of course we have to check which interactions are still left uncovered and all that stuff. But it's just the runtime in generating the row, whereas the exhaustive search was a big O of 2 to the k. If there are 2 values, I mean. So clearly the first one is a winner. But the thing is, it's only a heuristic because you're only making a local computation here versus just thinking about how well you're doing along the way. It's just a particular heuristic you can choose. It might be that maximizing the sum might be a better idea, but I don't know. There hasn't been much work on this, so it might be a really good project idea. And it's an open problem whether there's actually an exact method to figure out what the row would be that gives the maximum Hamming distance. Because here, you're not guaranteeing necessarily to get the maximum Hamming distance. You're guaranteeing that you're maximizing the Hamming distance along the way. But that's not necessarily the maximum you could ever obtain. Because once you choose a value in an early column, it will remain fixed. So it might have led to a bad choice if we had, say, a 0 or a 1 could be placed. So it might be a really good project idea to see, first off, how do we break ties? Whether we should do it randomly or something else, and whether there exists an exact efficient method, maybe to see how good you can actually get it. So if, for example, if you just generate a random row, and you just say do some number of iterations and just pick the row that has the minimum Hamming distance or maximum sum, and just see how good you actually get in practice. That might be a good project idea too. So there's a lot of things that you can do here. Okay, any questions about anti-random? Okay, so let's talk about IPO. So this is actually I guess a recent research topic, so it's not really truly well understood, but it's something to really look into. And there's actually quite a bit of work on it, but there's still not a really good consensus of what is the performance of IPO. So what is IPO? So the idea is that you have, if I can draw a straight line, we have a covering array right here. So I'm asserting to you that this is a covering array. I guarantee it to you. But if we say want to add a column, maybe we need another factor in our system to work with, then the question is, I want to add a new column onto this, onto this array, and I want the array to be, again, still as small as possible. So if I add this new column, then it might be that we need more rows. So because of the fact that we added a column, we may need more rows in here. And of course, the question is, or actually two questions. What good strategies are to actually fill that column? And the second strategy is, if we know what the best thing to do is in that new column, how do we add new rows to cover any interactions? Well, the good thing is, if you have an interaction that involves columns only within the original array, you don't have to work with them anymore. Because the array itself is a covering array by assumption. So the only interactions that matter are the ones that involve that new column that you just added. So that means that instead of looking at interactions of size t now, here we only have to look at interactions of size t minus 1 among the original columns. So 1 in the new column that we just added, and t minus 1 other ones. So that's why you see a k choose t minus 1 way down here versus a basically k choose t if we just looked at every possible interaction. So actually testing whether the new column allows you to still get a covering array is much faster. Because here, so let's actually look at this. So here, well, k choose t minus 1 is asymptotically the same thing as k to the t minus 1 v to the t. So the v to the t is the same, but the k choose t minus 1, that's the asymptotics of what k choose t minus 1 is. Whereas the one down here, this is asymptotically k to the t, v to the t. So we're actually, if we have a lot of columns, this is a big savings. So here, the runtime to actually check if the array really is a covering array is far faster than if we just looked at every interaction. So this is actually really good. But the thing is, that assumption requires that the original array is not modified. Because if I modify the original array, I might have to check an interaction that the t minus 1 interactions don't account for. So if I say modify this array, this entry right here, I may need to look at an interaction that involves the original columns, and So I don't want to modify the original array if possible. So what are the stages here? So the two stages it's really simple. We do what is called horizontal growth, which is adding the new column in the first place, however you want to do that. And then once you add the new column, then we have vertical growth, which is adding the rows at the bottom to account for every interaction that wasn't covered before. So the question is, of course, how do you choose the values in the new column, and how do you actually make the rows at the bottom? So the consensus is that the vertical growth is best with density or some other greedy method. So that's what the consensus seems to be of trading computational time with the number of rows actually produced. Yeah, and for horizontal growth, the consensus seems to be density is good, but not great. The better way that some people have tried is to do an exact search. As I said, there's a ton of literature on this. It's actually quite amazing how much literature there is on this particular algorithm, this approach. So the exact search, what do I mean by that? Just look at every possible column that you could ever place, and then just pick one that works. That covers many interactions and leaves few to be covered at the bottom. And so there are actually some other methods that for the horizontal growth. What people have tried is actually a random search. So what they do is they randomly add a column, and then once they find one that works and doesn't need new rows, they put it in and then repeat. So they try to pick a column randomly and then keep adding columns as they can until they actually need new rows. So that's what actually really recent techniques have tried, and that might be worth looking into. One thing that is actually a really good project idea and no one has tried, so hint, hint, this is a really good idea, is what if I chose two columns to add at the same time? Whereas this method says, we're going to add a column, fix it, and then add a column after. What if I add two columns at once? Right? What if I had three columns at once? What if I had four columns at once? Is there some type of pattern as to whether two columns are better or three columns are better or four or whatever? So that hasn't been actually tested and is really worth looking into. Yeah?
Wouldn't that still, I guess, on time whenever the same amount of work with just adding one column?
Exactly. So the runtime is effectively the same, but you get the advantage of making good choices in both columns simultaneously, whereas before you make choices in one column and then the choices for the next one are hinged on the previous column that you just worked with. Whereas here you can do both of them at the same time so they can work together. Whereas, and if you add more columns, well, the computational cost starts to get up more and more because you're adding more columns. But the columns can work together to make really good choices at each point. So yeah, so that's why I think this is actually a really good idea. And what I was able to do was some of the bounds for covering array sizes, you can improve them by adding multiple columns at the same time. So there is some evidence that this really does work, but it's just, I haven't done it, I haven't implemented this myself, and I don't think anyone else has either. So this is actually a really, really, really good project idea. Okay, any questions about that, about how IPO works? Okay, this is the last slide. So yeah, so the vertical growth is one row at a time. That's pretty much settled. Because it just basically just hinges on how many rows can I add in order to cover these set of interactions? Well, that's just basically every greedy algorithm we just ever talked about. You could try an exact method. So one thing that is also worth mentioning is for higher index covering arrays. What I recently just did was, what you can do is to make a covering array with lambda equal 1, so everything's covered once. And then what I do right after that is, once that array is fixed, I try to add some more rows right here to have every interaction covered twice, and then maybe another set of rows to cover things 3 times, etc. So what you can do is, for IPO, is to try to have these in a bunch of stages. So, and some papers actually have done this recently, where you, instead of having one method make the rows at the end for IPO, you have one algorithm make a few rows and then another algorithm make more rows. And so there's actually some kind of consensus of, from what I was able to find at least, of which algorithms you should use and how many you should use. Instead of just using one, you can use many of them. And you can actually get some improvements based off of that. Yeah, so that's also a really good project idea. There's no shortage of project ideas here. There's plenty of things that need to be done. Yeah, so horizontal growth is also greedy, and the order actually matters. So when I said that we were adding a new column over here, well, we have one entry in the first row, one entry in the second row, one entry in the third row. Which order should you process those in? Because the covering array is fixed, it seems that there's some entries that are more worthwhile to look at than others. And once you fix an entry in that new column, now the other entries are gonna have to depend on that choice. So would a random ordering be better, or top to bottom, or bottom up, or no one really seems to know what the best is here either. So yeah, so that's also something to look into. Yeah.
Let's see. What about like kind of doing that?
Diagonally, I'm not sure. Oh. So, oh, okay,
So
huh.
maybe you add, so you start with like one value, and then maybe
Okay, so let's actually look at this, because I haven't actually thought of that. So covering array. So
basically your base covering array is just like one value, and then you would add a value to the right of it and a value on the bottom. So you're kind of creating one column and one row, but then you can finish that second.
oh, simultaneously.
Yeah.
I haven't thought of that. That's actually a really good observation. I don't think anyone else has either. So let's actually look at this. So what you're saying is that,
It's like you start with like 1, for example.
okay, so
You would start with 1 digit, and then you can go with that. You can build onto. You make another row by add to the row where 1 is on by adding some other number, and then you add something to the bottom, and then you complete that, so you have a 2 by 2 covering array.
okay, so like if I have a 0, say like right here, what are you saying to do?
No, I mean I was thinking like upper left corner.
Okay, so like let's just say 0's up here. What do we do?
You add, I'm guessing, let's say you add like a 1 to the right of 0, and then you add some other number to the bottom of 0.
Oh, okay. Oh, I see what you mean. So like starting from nothing.
Starting from nothing.
Okay, so 0, yeah.
And then you add something to the right of 0, and then to the bottom of both of those.
Okay, yeah, so like
And
1
then
0.
then you have something right there, and then you do the same thing where you add another item to the row with 0, 1.
To both rows, you mean?
Essentially both rows. Yeah.
Okay.
You're increasing the dimensions.
Yes, so 0, and then maybe
1.
then 1 or
And
something.
then you basically have to add another row underneath.
Yeah, okay. Yeah, so then like say I put 0 0 here, and then I put a 1.
Yeah.
Yeah, no one's looked into this. That's an awesome project idea. And to see like which method to use at each point, and whether, yeah, that's actually a really good project idea. Yeah, everyone write that down, because that is absolutely some, unless you want to take it.
I think I'll claim them. I'm gonna like reserve this.
Okay, so Bilal
I mean,
claimed it.
It's my shopping cart.
Okay. Yeah. So this is the point of having discussions like this, because we can stumble across things that are new. So any other questions about anti-random or IPO? None? Okay, so I'll see you on Wednesday.